In this section, we're going to look at the carbonyl group. So the carbonyl group is characterized by a carbon double bond oxygen attached either at the end or within the middle of some hydrocarbon. Now, to understand this a little bit in more detail, we need to understand exactly what's going on with the electrons. So normally oxygen in group 6 would have 6, but what it's done here is it's accepted a dative pair of electrons from the carbon. And so the carbon, which has 4 bonds normally because it has 4 electrons in its outermost shell, it actually gives oxygen a pair of those electrons datively, and that creates this double bond. It means that the oxygen now has a full outer shell, having 4 electrons in lone pairs and having 2 bonding electrons and having 2 dative electrons, which creates this double bond. You can see that having a full outer shell would make oxygen inert. It's basically got a noble gas-like outer shell now, but you can see also that the presence of those electrons there, denoted by those crosses, means that this end of the molecule would be negative, with a negative dipole. It also means that the carbon adjacent to it would be positive. And though the oxygen itself is very inert, the presence of the oxygen makes the carbon susceptible to nucleophilic attack. So let's have a look at a very simple carbonyl group. So this is aldehyde, and this most simple one is called methanal. Now look at how we represent an aldehyde in the naming convention. So it's, as usual, it's the meth, eth, the prop, that sort of part at the beginning, but it's anal at the end to represent that it is an aldehyde. Now the most simple one, methanal, is what we used to call formaldehyde. It's a carbon-oxygen double bond and just a single pair of hydrogens. Now, strange enough, this chemical is very useful. It can lock proteins in place, and it's the degradation of the proteins that normally leads to decay of living tissue. Locking them all in place means they physically can't decay. And so what we can do is we can preserve organic tissue in a bath of formaldehyde. And if you go into the spirit room of the Natural History Museum, you'll see they have everything from hippos down to insects preserved in formaldehyde. And it's a kind of a yellowy, quite strong smelling liquid. You don't get it on you because it is a carcinogen, and if breathed in, it can cause severe breathing difficulties. But it has a very, very distinctive smell. Another place where you might have seen it is in surgeon museums or museums of medical history, because anything that's unusual that's been removed from a human body can again be preserved in formaldehyde. And this property lends its use in art. Damien Hirst, a famous artist, one of his artworks involved preserving various different interesting animals in formaldehyde. And so you can see behind him, stood in front of a shark. Now, the yellow colour of formaldehyde has been hidden here by putting blue-tinted glass in front of the thing, but trust me, it is formaldehyde. Now, another example, you can store parts of human bodies. Here, pathologist Dr. Thomas Harvey with a bottle, and within that is Einstein's brain, which was removed without permission, but then kept in a jar so that people could study it, finding that Einstein's brain was largely the same as anybody else's brain. It was how he used it that was different. So the aldehydes, they start with methanal, with a single carbon, and then ethanal, which is 2 carbons, and propanal, butanal, etc. Now, how they are made, here we can see that the manufacture of them comes from something like this, the C3OH. It's a primary alcohol in that the OH group is on the end. If we oxidize it, then what we can create is these aldehydes. So we get rid of the hydrogen, and we get then a double bond forming to that end oxygen. And that is how we make an aldehyde. The heavier aldehydes are mainly manufactured as intermediate steps in the synthesis of other things. And so we don't have any great use of some of these chemicals. They are useful for the construction of more complex chemicals. But some of these aldehydes actually are made naturally. In nature, we find them. Octanal is the chemical that gives oranges their distinctive scent. The smell and therefore taste of oranges is largely due to the presence of octanol, this aldehyde present in the fruit. Now, if we want something to taste or smell like oranges, we don't have to get oranges anywhere near it. All we need to do is put in some octanol. Now, for things like soft drinks and confectionery that is orange flavoured, the main source of this octanol is not oranges. It is in fact synthesized from hexene, which, as you know, is a hydrocarbon that derives from crude oil. So when you get that nice orange flavour of a fizzy drink, it's actually a derivative of crude oil that has made it taste like orange and nothing to do with oranges. A different member of the carbonyl family is the ketone. A ketone is similar to an aldehyde, still has a double bond oxygen, but this time it is not on the end of the chain, it is in the middle somewhere. It is joined to two carbons. Now, the strange thing about this is having that CO group in the middle, it interacts with our olfactory receptors in our nose. It means that, especially the longer ketones, they tend to have a floral scent, which makes them very useful as an additive in food. But the most simple ketones include things like acetone. That's the most simple one, and that is what you put on your nails to remove your nail varnish. It's also very good as a solvent for removing things like superglue. When protesters superglue themselves to the road, the police just come along with a nail varnish remover and unstick them. In the terms of naming ketones, it makes no sense to talk about the ketone with a single carbon, or even in fact with a double carbon, because there'd be no way of distinguishing it from the acetone of the same size. For example, ethanone with two carbons, if you attach the double oxygen bond to one of those carbons, it would have to be at one end or the other. There's no middle carbon or middle of the chain carbon to attach it to or in between. And so, therefore, something like ethanone, for example, is going to be exactly the same as the aldehyde, ethanal. The ketones only come into their own when we get to the three-carbon version, propanone, and butanone, and pentanone, which is quite difficult to say. And so, here, you can see in all of these are here, but in the naming convention, if it was attached to the end, it would be like pentan-1-one, but we'd never call it that, because if it was attached to the end, it would no longer be a ketone, it would be an aldehyde. The only ketones we see are things, long-chain ones, with numbers 2 or more. So in this case, pentan-2-one is on the second carbon. We could also have pentan-3-one. The next one along would be pentan-2-one once more, and then we couldn't have one on the end without changing it back into an aldehyde. Now, we can make these in a similar process of oxidation that we did to the acetones from alcohols. This time, though, we need the oxygen already to be placed on one of the middle of the chain carbons. So it would have to be a secondary alcohol, where the OH group is not attached to the end, but onto one of the middle carbons to do it. A quick detail, how can we distinguish an aldehyde from a ketone? Well, obviously with the carbon chain of 1 or 2, we can't, because they're actually the same molecule. It's only when we get to the third, 3 carbons in the chain, do we actually see some kind of way of distinguishing them. Now, the standard test for this, and one you need to remember, is aldehydes can be oxidized by carboxylic acids when refluxed with potassium dichromate. And sulfuric acid. So it's a bit of a mixture, but after addition of equal amounts of this thing, potassium dichromate, K2Cr2O7, acetone remains unreactive, but benzyl aldehyde becomes oxidized. So basically, the ketone is not reactive in this instance, it doesn't change color, but the aldehydes do. And that is the standard test for figuring out, do we have a ketone or an aldehyde? Okay, let's have a little look at the double bond that forms between the carbon and the oxygen, and actually take a step back first, and let's look at double bonds in general. If we look at a carbon double bond, like we would find in ethene or an alkene of some sort, you can see that it forms by the overlap of the sigma orbitals of one set of electrons, and then the formation of pi bond orbitals above and below the dynamo, and that's what stops it from being able to rotate. And because the carbons on either side are identical to each other, it makes it non-polar. There's not one side with a dipole plus or minus. in that situation. However, we're now talking for aldehydes and ketones with a carbon-oxygen double bond. And what we have here is we have the same formation of a pi and a sigma bond, but what is different is the oxygen has this two sets of lone pairs on the end. It means that it is quite electronegative, whereas the other end is quite electropositive. So we've got a dipole moment form across the two. Now, nucleophiles, those things that would attack or be attracted to positive charge, are going to undergo nucleophilic substitution or addition with the carbon. And so this, having this double bond oxygen there makes this whole molecule susceptible to negatively charged reagents. So there are two types of nucleophilic attack that I want to talk about, and they're important because they're going to give us the machinery for understanding how we can synthesize larger chemicals. So the very first one I want to talk about is how we can increase the length of a carbon chain. We can actually use these properties of a ketone or an aldehyde to make our carbon chain much longer. And we start off with a chemical called hydrogen cyanide. It's a famous poison. It's found in apple pips, and it's used to make short carbonyl compounds into much longer ones. So here we've got propanol, and you can see what I've drawn on it is the positive and the negative end of that carbon double bond. And there's hydrogen cyanide, which is HCN, though it's displayed here NCH, same thing. And what we're going to do is we're going to subject it to a sulfuric acid and a sodium cyanide bath. And what's going to happen is the hydrogen cyanide, the hydrogen is going to, in the acidified solution, dissociate, and the carbon-nitrogen triple bond is then going to form a carbon-carbon bond onto the carbon adjacent to the oxygen. It's actually going to, the double bond is going to break on the oxygen, and it's going to allow the carbon to now bond with the CN minus with the negative charge that it is carrying. The oxygen whose double bond is now broken can now form in the acidified solution a bond to the hydrogen ions that are present. And so this is how we could make a situation. Now what that has basically done is it's created like a tail of carbon that now goes past that oxygen double bond. And so with further reactions I could now make this whole chemical a longer chain hydrocarbon. Now this particular one, 2-hydroxy butyronitril, very difficult to say, is actually one of the chemicals that we need to create to form the monomer for perspex. So what we're now seeing is that these chemicals, which a second ago were just smelly things for getting your nail varnish off, are actually some of the raw ingredients for some of the plastics that we use every single day. Now, we can do things with our carbonyls, so both aldehydes and ketones, they're both made from alcohols. The aldehydes are made from the primary alcohols with the OH group on the end carbon, and the ketones are made from the secondary alcohols with the OH group attached to those carbons that are middle of the chain. Now, what we can do, though, we can synthesize them via oxidation from the alcohols. Can we oxidize them further? And we can with the aldehydes, because if we subject them to further oxygenation, then what we would get is them forming a COOH group, carboxylic acid. The ketones though are much less reactive, and so under these same conditions they just tend to fall apart. So we can't further oxidize the ketones, but we can the aldehydes. Now let's look at the reverse process. If we can add more and more oxygen to these, can we take oxygen away? Can we make them undergo reduction, go backwards, back into their alcohols? And yes, indeed we can. But what we need is a reducing agent. Now the reducing agent is basically acting kind of like a catalyst, I suppose, but it's going to come in and it's going to donate one of its hydrogens to undergo nucleophilic substitution. It is from this chemical here, sodium tetrahydroborate. That's probably pronounced wrong, but NaBH₄. One of the hydrogens of this is going to become the nucleophile that we need to attack the carbon to reduce these and deoxygenate the chemical. So let's take a look at how it works. one of the hydrogens becomes attracted to the electron deficient carbon. So what we can see, it comes in, and then what happens is the electrons in that double bond breaks and gets returned to the oxygen, making it O-. So it comes in, it goes for the positive charge of the carbon, breaks the electrons in the double bond and removes them over to the oxygen, and it creates an intermediate step which is strongly attractive to other molecules like the H+ in water. So in trying to turn our carbonyl back into an alcohol, we put in this reducing agent with it, the NaBH₄. One of the hydrogens becomes a nucleophile, attacks the carbon. The electrons get removed onto the oxygen, making it a single bond to the oxygen. But the oxygen, now carrying a negative charge, creates a very, very polar intermediate. And that polarity, that strong negative charge on the oxygen, is very, very attractive to the positive dipole of a water molecule. And so what happens is the electrons of the water molecule to one of those hydrogens is removed onto the oxygen, forming the OH- group, and the hydrogen that is disassociated from the water then comes and joins onto the end of this intermediate step onto the oxygen. And so this forms the OH group on the end, meaning that this propanone has turned back into propan-2-ol. It has reduced back into an alcohol. Now this is interesting because it shows how we can make them and we can turn them back again, how it is reversible. But the main reason why we are required to learn this is because it's one of the very best examples of nucleophilic addition. And so other places where we have to think about nucleophilic addition, well, the halogenoalkanes, where we attach these react with the nucleophiles OH-, CN-, NH3, producing alcohols, nitriles, and amines. So that's something that we probably did in year 12. This cyanohydrin formation, carbonyl compounds getting longer with hydrogen cyanide. That's a very good example of nucleophilic addition. It's the one we looked at before. The hydrolysis of haloalkanes, substituting with water OH gives alcohols, and the formation of amines. So these are 4 different places in A-level chemistry where we need to be able to understand and apply nucleophilic addition.